Next, we're going to do an extension of Markov chains. This is a technique that is frequently used in ecology. And instead of a transition matrix, we're going to introduce what we call a Leslie matrix. Here's an example with populations of female birds. We look at female birds because they're the ones that reproduce. These birds can live up to 3 years, so they can be age 0, age 1, or age 2. And we look at the survival rates. So to survive from age 0 to age 1 is pretty difficult. There's a 20% survival rate there. And then to survive from age 1 to age 2 is a little bit easier. Still pretty brutal, 50% survival rate. And then for the age 1 birds, they can produce 3 offspring during mating and birthing season. And then age 2 birds are a little bit better at that. They can produce 6 offspring. They do that and then they die. Brutal realities of nature. We can make a matrix for this. We put age 0, age 1, age 2 birds, age 0, age 1, age 2 birds, and it's kind of like a transition matrix for a Markov chain. So, if you're age 0, you can't still be age 0. You have a 20% chance, or 0.2 probability, of being age 1. You can't skip to age 2. If you're in age 1, you can't stay age 1. You have a 50% chance, or 0.5 probability, of getting to age 2. And you're going to birth 3 offspring. So there's a 3 there. And for age 2, you can't go back to age 1, you can't stay age 2, you're actually going to die, but you leave behind 6 offspring. So we call this a Leslie matrix. This is not a transition matrix because the columns do not sum to 1. That's the thing that prevents it from being a transition matrix. Okay, so let's see what happens. Well, we can start with a population. Let's say in year 0, the female bird population is 3,000. There's 1,000 of each age. 1,000 age 0 female birds, 1,000 age 1 female birds, and 1,000 age 2 female birds. Then we could just multiply, same thing as usual, multiply the matrix by the column vector on the right, and then we're going to get these results. So suddenly there's 9,000 age 0 birds, only 200 age 1 birds, 500 age 2 birds, and then in the second year evens out a little bit more, 3,600, 1,800, and 100, and then in the third year we get 6,000, 720, 900, so we could keep going, but we don't really know what the pattern is going to be. We might see one as we get bigger. Or we can just start doing linear algebra on this Leslie matrix. So if we calculate the eigenvalues, I'm going to put approximate, because these are long decimals, and if we express them in radical form, it wouldn't even be worth it. Very ugly. 1.0759 is the real eigenvalue. We've got 2 complex eigenvalues. Negative 0.5380 plus or minus 0.5179i. So 3 distinct eigenvalues, 1 real, 2 complex. Notice that this eigenvalue is greater than 1. And if we calculated the magnitude of these guys, of the complex ones, these would have magnitude less than 1. Okay, so what happens here? Remember this, so if we call this matrix A, then we could decompose A into V, lambda, V inverse. That wasn't specific to transition matrices. We can do this with any matrix, certainly any matrix with distinct eigenvalues. A couple more matrices as well. And so then when we went to A to the n, where n is pretty big, this was V, lambda to the n, the inverse, and then lambda was a diagonal matrix with the eigenvalues on the diagonal. So since these guys are magnitude less than 1, if we raise them to a big power, they will go to 0. If we raise this to a big power, this will actually keep growing. So we say that this is our growth rate, meaning from year to year, approximately, the population grows by this much. Maybe not so much in the beginning, but eventually it will tend to this. And then we can find the eigenvector corresponding to this eigenvalue. Sorry, I'll put approximately equals again because they're going to be ugly decimals. 0.7860, 0.1461, and 0.0679. And this is going to give us the ratios of the ages in the end behavior. So since the population is growing, there's never a steady state with exact numbers, but there will be a steady state of ratios of the ages. And it'll meander a little bit before it gets close to this, but eventually it will. So that's pretty similar to Markov chain, but we use what we call a Leslie matrix.